A laptop works perfectly at one desk. Then, a user carries it into a conference room, and the meeting falls apart. Nothing is unplugged. No switch port went down. But the wireless network changed anyway, because the cable is now the room itself. Air, walls, metal, distance, other radios, and every device competing for a chance to talk. That is the first mental shift for wireless LANs. Ethernet and 802.11 both live at layers 1 and 2. Both define how devices share a local medium and move frames across that medium. But Ethernet usually gets a bounded path. Copper or fiber keeps the signal inside a controlled cable. Wireless uses an unbounded medium. The signal radiates through space, and every station in range can hear it. That freedom is why wireless is useful. Users can move. Phones, tablets, scanners, printers, and laptops do not need a cable at every spot. But the same freedom creates the design problems. Anyone nearby can receive the signal, so encryption matters. Devices cannot all transmit at once, so they contend for airtime. Neighboring networks, Bluetooth, cordless phones, microwave ovens, and other sources can interfere. Regulatory bodies control what frequencies and channels are legal. And coverage becomes a real engineering question, instead of a cable length check. Wireless is half duplex. Client cannot transmit and receive at the same time on the same channel, and two transmitters can still step on each other. Ethernet hubs used CSMA/CD, collision detection. Wireless uses CSMA/CA, collision avoidance. 2. A station listens first. If the channel sounds busy, it waits a random short time and tries again. If the channel sounds clear, it transmits. The exam point is not a packet capture deep dive. The point is that wireless tries to avoid collisions because detecting them over the air is not reliable the way it was on a shared wire. Now walk the building with the user. In one room, the signal is strong. Around the corner, it drops. Behind a metal elevator, it almost disappears. That is wave behavior. Absorption weakens the signal as energy is converted into heat, like a wall eating part of the radio wave. Reflection bounces energy off surfaces, especially metal. Refraction bends a wave as it passes between materials. Diffraction bends and spreads a wave around an obstacle. Scattering spreads energy in odd directions when the wave hits irregular surfaces, dust, water vapor, or textured material. You do not need to design a full radio survey for CCNA, but you do need to recognize why wireless coverage is messy. Radio frequency gives us the next decision. An antenna creates electromagnetic waves. The amplitude is signal strength. More amplitude means more energy for the receiver to distinguish from background noise. Frequency is how many times the wave oscillates per second, measured in hertz. 1,000 hertz is a kilohertz. 1,000,000 is a megahertz. 1,000,000,000 is a gigahertz. Wireless LANs use gigahertz bands. The practical trade-off is simple. Lower frequencies travel farther and penetrate obstacles better, but they are usually more crowded and support lower rates. Higher frequencies can support higher data rates and may be less crowded, but they are absorbed more easily by walls and distance. That is why 2.4 gigahertz often reaches farther, but feels congested, while 5 gigahertz and 6 gigahertz can be cleaner and faster, but need more careful coverage planning. The 2.4 gigahertz band is the classic trap. It has 14 channels in the standard, though not every country allows all of them. Many of those channels overlap. If neighboring access points use overlapping channels, they interfere and waste airtime. In the United States and Canada, the common non-overlapping pattern is channels 1, 6, and 11. In some countries, 1, 5, 9, and 13 can also be used. For CCNA, remember the main story. 2.4 GHz overlaps, so channel planning matters. The 5 GHz band is different. With normal 20 MHz channels, the channels do not overlap, which makes multi-AP planning easier. Channels can also be bonded into 40, 80, or 160 MHz widths for higher throughput. But wider channels mean fewer separate channels to reuse. The 6 GHz band adds even more spectrum for modern wireless LANs, including Wi-Fi 6E and Wi-Fi 7, and can support very wide channels. It is newer and less crowded, but still governed by device support and regulatory rules. The standards map onto those bands. Original 802 by 11 and 802 by 11B use 2.4 GHz. 802 by 11A uses 5 GHz. 802 by 11 gram uses 2.4 GHz. 802.11n, marketed as Wi-Fi 4, can use 2.4 and 5 GHz. 802.11 AC, Wi-Fi 5, uses 5 GHz. 802.11 AX, Wi-Fi 6, uses 2.4 and 5 GHz. And Wi-Fi 6E extends 802.11 AX into 6 GHz. 802.1b Wi-Fi 7 can use 2.4, 5, and 6 GHz. 802. The exam likes these band mappings because they explain real channel decisions. Once the radio choices are clear, think about how clients join a wireless LAN. A service set is a group of wireless devices sharing the same SSID. The SSID is the name users pick from the wireless list. But the SSID is only the human-readable name. A BSSID uniquely identifies a basic service set and is usually the MAC address of the AP radio. The simplest service set is an IBSS, or ad hoc wireless network. Clients talk directly to each other without an access point. It can work for a quick temporary setup, but it does not scale like a real enterprise WLAN. Most networks use a BSS instead. In a basic service set, clients associate to one access point. The AP coordinates wireless access and bridges traffic toward the wired network. That wired side is the distribution system. In practice, the AP usually has an Ethernet uplink to a switch. The AP bridges between 802.11 wireless frames and Ethernet frames. It may map different SSIDs to different VLANs, such as staff and guest. One AP can provide multiple BSSs, each with its own BSSID. But if those BSSs share one radio, they also share one channel and one pool of airtime. More SSIDs do not magically create more capacity. A single AP is enough for a small office or home, but enterprises need coverage across a floor or building. That is an extended service set. An ESS links multiple BSSs through the distribution system. Each AP has its own BSSID, but they share the same SSID, so users see one network name. As a client moves, it roams from one BSS to another. For that to feel seamless, cells should overlap enough for the client to hear the next AP before the old one becomes unusable. And neighboring APs should use non-overlapping channels. Sometimes Ethernet cannot reach every AP location. A mesh basic service set connects APs wirelessly. One AP connected to the distribution system is the root access point. APs that relay through the mesh are mesh access points. Mesh can solve cabling problems, but radio resources become precious because the network may need one radio for clients and another for backhaul. With only one radio, performance can drop sharply. Other AP modes solve specific physical problems. A repeater extends a cell by receiving and retransmitting wireless frames, but it uses extra airtime and can reduce throughput. A workgroup bridge lets a wired-only device connect through wireless by making the bridge act like a client of the main AP. An outdoor bridge connects separate LANs across distance, often between buildings, using directional antennas and clear line of sight. So when the exam gives you a wireless scenario, do not start by memorizing acronyms. Ask what problem is being solved. Is the air crowded, so channel choice matters? Is distance or a wall weakening the signal? Is the client roaming across multiple BSSs inside one ESS? Is an AP connecting wireless clients to the distribution system, repeating coverage, bridging a wired device, or linking two buildings? Wireless LAN fundamentals are not magic radio trivia. They are Layer 1 and Layer 2 decisions, made harder because the medium is open air. Quick recap. 802.11 defines wireless LAN behavior at layers 1 and 2. Air is an unbounded shared medium, so wireless has privacy, interference, airtime, regulation, and coverage challenges. Wireless is half duplex and uses CSMA/CA to avoid collisions. Wave behavior includes absorption, reflection, refraction, diffraction, and scattering. Amplitude is signal strength, and frequency is oscillations per second. 2.4 GHz reaches better, but overlaps, and is crowded. So use channel planning such as 1, 6, and 11.5 GHz has non-overlapping 20 MHz channels and supports wider channels. 6 GHz adds newer, wider spectrum. Know which 802.11 standards use which bands. IBSS is ad hoc. BSS uses one AP. ESS links multiple BSSs through a distribution system for roaming. And MBSS uses wireless AP mesh links. Repeaters extend range. Workgroup bridges connect wired-only devices, and outdoor bridges connect LANs across distance.